welcome to the next lecture on network analysis, and we have been discussing in last few lectures about the application of graph theory to network solving. Now, if you recall that given a network, we will first draw the graph of the network, and then from graph of the network we will draw a tree, and then from tree I can also get the number of twigs, number of links, and based on that different techniques, different important relations were found out. But really we have not solved the network problem, a given network problem for finding out the currents yet, we have not done. What simply we have done is this: we have found out these three basic relationships that I will rewrite here, that is A into I e is equal to 0, that is KCL. A is the incidence matrix, and then we found out that A transpose B nodes equal to the element voltages. This is one relation we found out. This is A is called the incidence matrix. And this A matrix we will get in touch with for a given graph when I want to solve the network in nodal analysis. This is essentially the KCL equation. Similarly, we got another two interesting relations, that is B into the element voltage matrix. This is equal to 0. This is KCL, this is KVL. B V equal to 0, and also we have seen that B transpose the loop currents is equal to the element currents. And we have discussed at length how to get A P matrix from a given network. So, I L is the number of fundamental loop currents. And finally, we got a relationship like Q into, and this is called incidence matrix, this is called cut set, tie set matrix, this is tie set. Cut set I am going to write tie set, and this is called this Q into I E was equal to 0, this is called cut set Q matrix, and this is also KCL, but KCL at not nodes, KCL at fundamental cut set, fundamental cut sets. This we have all discussed, and then finally we got this Q transpose into the twig voltages is equal to your element voltages. In last few lectures we developed this. Now, any of these methods looks like can be applied to solve the circuit. So, this 6 direction is IE6, henceforth I will simplify this. I am not going to write IE6, IE5, it means IE3 in this direction, IE5 in this direction, and so on. These are the nodes. Now, today what I am going to do is this: how do I get the exactly how I am going to solve the network problem. Now, in general, this network, this branch, for example, branch 6, it will contain in general some impedance, some sources as well, and it is true for all the elements. That is what I mean to say is this, if I draw, that is this is suppose the given network, which is actually given is like this. Suppose some impedance is there, then some voltage source is there. This is, suppose I say it is Z1 and this is Vs1. This point is A, this point is O. This branch, and this is I have specified as 1 branch number, got the point. And in general it could also have a current source in parallel, IS1. So, this line, although I have just drawn a single line, in general in this line there will be an impedance, there will be an impedance and there will be sources, voltage source and current source as connected here. Similarly, here in this branch, there will be, say, branch number 4, you can have an impedance, you can have another voltage source, Vs4, element 4, and there may be a current source here. IS4. Got the point? And similarly, in this branch, so then this branch should also have a voltage source. Where is the arrow given? This way arrow is given. So, it can have an impedance Z2, because this branch number is 2 and there will be some Vs2 and this is a plus, and there may be a current source in parallel with this element. Okay. So, current was going like this. So, this is the thing, IS2. Similarly, these two branches will have impedances. I am not drawing that. Got the point. Therefore, this branch 6, between these 2 points, what may exist in general is a voltage source, is an impedance in series with this. So, there are something here. What is this box? This box is this. There will be an impedance there, but while drawing the tree of the network, we have considered this to be one thing and drew a horizontal line like that. Therefore, to find out, and this current I am telling IE4, mind you, this current is IE4, not this impedance current. Got the idea? And this voltage between this to this point is V4, etc. Here I am not completing this in order to 1, 2, 3 branches I have drawn, another 3 branches similar things. Therefore, now the question is, I have only told you that for a graph you do not show all these details, you just draw lines and say that this current is IE6, that is what I told, and this voltage you assume this plus minus to be VE6, and similarly for the other elements of this graph. Now, today what I am going to do is this, I am going a step forward, that is okay, these are the relations which exist between these element currents and the voltage across this whole combination. then how really I am going to solve a network problem? That is the thing. I think you have got the idea. So, next point is, first suppose, and this method, mind you, this B matrix will come into picture when you want to solve this circuit, solve for the fundamental loop currents I L. Okay. And this one is nodal essentially, and this one is loop analysis of circuit. And this one is also like nodal, but slightly different, and it is called Krsat method. So, first let us try to give in a network, I want to solve it by loop analysis. So, I will now go here. So, want to solve a network problem by fundamental by loop analysis. What I am going to do? So, first thing is a general kth element looks like if the arrow you have given like this, between two nodes an element exists. So, I will say this, you carefully follow me. So, here is your, I will say this is JDK, the impedance. Let me not put the arrow first. This is JDK, and then there may be a voltage source. This arrow is known. So, always put, I will follow this convention, the source with this polarity is connected. So, these are the two nodes, and here is a current source. In parallel, and these two are the nodes, mind you. This is kth branch, k is equal to 1 to 6, put all the branch will be there, and if you put k equal to 1, then this node is A, this node is B, and so on. You have understood me. So, this is the thing. Now, what I am telling, while say for a particular node, say node 4, this is the arrow, suppose k equal to 4 you substitute. So, the polarity of the voltage will be like this, plus minus this E4 voltage, and IE is this current, is IEK. This you must understand. Henceforth, this picture I kept behind the scene. I just replaced this whole thing by a line to understand what are the relationship of this current with different matrices like KCL, this, that, and this is inside this, in this particular element, this box was replaced by a line, but this box in general may contain like this. What is ISK? ISK is a source current in kth branch, in kth element. What is VSK? Source voltage. In kth branch, in kth element. This is the thing. So, when I ask to solve a network problem, I will be interested to know what are the currents flowing in JDK. This IK is the total current here. Understood the point? If you just allow me, I will make one correction here. Always I will assume current is injected in the positive terminal of the node. ISK direction is like this, and also polarity of the VSK is this arrow decides what is. If the arrow is coming like this, plus is there. So, this you please follow. Then I must find out relations. Now, first thing is I want to solve this problem by loop analysis. Loop analysis means that tie set matrix will be invoked, that is this one. You want to find out the loop currents. Okay. So, first of all you see that, so ISK is the source current and this one. So, ISK arrow, this arrow I will put so that it also injects current like IEK. IEK is those currents which we have already found out relations with, is not. So, this is the thing, and this is the voltage across this element. VEK is this voltage, mind you, VEK is this voltage, and we assign plus here, minus here. That is, for this element, this is plus, this is minus, and this is VE6, and this is IE6. So, IE6 comes, but inside this actually this I can expect. In some branches only impedances will be present, then VSK will be 0 and ISK will also may not be present in most of the cases. Few branches will have impedances, but in general this will be the thing. Now, you see the current flowing through this branch will be ISK plus IEK, apply KCL here. So, this current is IEK plus ISK flowing from left to right. So, there will be a voltage drop here, JDK into this current. So, you can see that VEK will be VSK, this to this plus, then plus this voltage drop. This voltage drop will be ZEK into IEK plus ISK, with this side plus this side minus. So, minus to plus, both the terms are added up. So, this will be equal to this elemental voltage. Okay. In case of mesh analysis, we would like to apply these equations. So, we would like to find out the in terms of loop current how things looks like, is not. So, what I will do is this, this is VEK and this can be broken up into two terms, that is ZEK into IEK plus ZEK into ISK plus VSK. Mind you, IS and VS are source voltages, they will be known, it is there. Therefore, it looks like I can, I will just show you, write this one like V1, VE1 will be in general JD1 I1, IE1, put k equal to 1, you get VE1 plus ZE2 IS2 present in why JD1 IE1 plus JD1 only, JD1 IS1 plus, if I miss a term point out, plus VS1. This will be the thing. Similarly, VE2, let me write once, JD2 IE2 plus ZE2 IS2 plus VS2. VE3 will be equal to JD3 IE3 plus ZE3 IS3 plus VS3. Finally, another for VE4, let me write at least once, so that ZE4 IE4 plus ZE4 IS4 plus VS4, V5 quickly let me write JD5 IE5 plus JD5 IS5 plus VS5. Finally, the last element for this particular problem, it will be ZE6 IE6 plus ZE6 IS6 plus VS6. Now, all these 6 equations can be written in a matrix form as this. So, so this one copy, next page. So, all these 6 equations can be written as in matrix form as these 6 equations V1, V2, V3, V4, V5, V6. This one can be written as JD1, JD2, JD3, JD4. It will be a diagonal matrix JD5 and JD6. All other elements are 0, and here you will have IE1, IE2, IE3, IE4, IE5, IE6. Other elements are all zeros. It is a diagonal matrix which the diagonal elements are nothing but the impedances of the several branches, and this is the elemental voltage. So, this into IE, this is the 6 plus, then you have the source things. Source thing will be also this matrix, the same matrix comes in here. I am not writing, that is this diagonal JD1 to JD6. You see JD1 into IS1 plus JD2 into IS2, and this column will be IS1 assuming all the branches are having current sources IS 4, IS 5 and IS 6, and this plus a column vector only, it has got no Z, which will have all the source voltages present. Got the point? This will be the equation. So, all the elemental voltages can be written as this tree currents, I mean element currents and some diagonal elements. These two are same, these two matrices are same, this is the thing. So, this whole thing therefore, can be written as, here let me write as a column vector of the element voltages, this equation I am writing. B is equal to, I will say it is J D I will write, where J D is the a diagonal matrix into the all the element currents I E plus J D into I S, where I S is a column vector having I S 1, I S 2, I S 3, I S 4 like that, plus a column vector of the source voltages. Got the idea? This is the in shorthand, this is the nice way of representing the things. Therefore, coming back to this previous slide, each element in general can have this form. So, I wrote down, and V k is this V k in the trees. So, and here there was a box, each element has a box, that box is this one inside. So, actual impedance current Z d k will be sum of I s k plus I e k. Okay. If you solve I e k, it is over. So, we will now discuss about that. So, we get up to this point. So, we write that this equation as, so we have got V E is equal to J D, a diagonal matrix, into I E, is it I E, plus J D into I S and plus V S. That is this equation, V equal to J D into I E plus J D into I S plus V S, where we should only remember that that this is a column vector, this is a diagonal J D, this is J D into I S, this is V S. V S is a column vector. Okay. Now, you see, in loop analysis what you do? These are what? Element voltages V 1, V 2, V 3, V 4 like that. Now, we multiply both the sides by B transpose, multiply, pre-multiply by B transpose B by B, pre-multiply both sides by B, then it will be equal to, thank you. So, this will be equal to, let me write in steps, B into V, this will be equal to B into J D into I E plus B into J D into I S plus B into V S. This is the thing. But what is B into V? B into V is 0. KVL equations. This is KVL. Terminal voltage in any loop sum up to 0. So, this is equal to 0 then. What I want to find out? My goal is to find out the element currents. So, I will write or B into J D into I E, then will become equal to, take these two terms on the right hand side, because these involve sources and these are known. So, this will be minus B J D into I S minus B into V S. This will be the thing. But in loop analysis, which I am trying to do, I must find out the fundamental loop currents, and I say if I know the fundamental loop currents, I have solved the circuit, is not. So, what is the next relation? Next relation that I will be using is B transpose the element currents can be expressed in terms of the loop currents. This is loop current, fundamental loop current. So, what we are going to do is here is B into J D, and for I E I will write B transpose into I L. About this fundamental loop currents I know what it means. So, this is equal to minus B into J D into I S minus B into V S. Now, this will be a square matrix, okay, and this is sometimes called loop impedance matrix. So, this one, if you call Z, is called the loop impedance matrix. So, this will be then equal to Z into I L. So, I L, the loop currents will be equal to minus, pre-multiply with this Z inverse, you multiply both sides with, and then minus Z inverse B J D into I S minus this Z inverse into B into V S. This will be the loop currents. This is extra, it is correct, minus. So, I will be able to solve this circuit. Now, I was always telling you that this graph technique is applied to circuit analysis just to solve a big circuit, because you see now I will be doing mechanically. Given a network, the formation of this J D is very simple, only put in the diagonals these elements. Finding out B matrix elements are plus 1 minus 1, that also I know how to do it, cut set matrix. And then I have to calculate this loop impedance matrix Z, which is this computation I have to do B J D B transpose, and then take its inverse and multiply. So, this problem can be delegated to a computer and loop currents will be obtained. Once the loop current is obtained, then what I am going to do? I will calculate after you get this, then I will say element currents is equal to B transpose into IL. I will be able to calculate this element currents, that is I 1, I 2, I 3. But I 1, I 2, I 3 are not the impedance currents in a particular branch, is not. I k you will get I 1, I 2, I 3. Okay, add with this source current. So, I e plus I s will give you actual impedance current I z d 1, for example, if somebody writes. So, after you, that is what I am going to tell. If you have solved the loop current, then you have solved the circuit. What else? You calculate I e. After you calculate I e, add to this plus I s to get the actual impedance current. Current through the current source is already known. So, then finally, if you say what is I Z 1, you will say it is equal to I E 1 plus I S 1. In other words, if you say the current flowing through that impedance, if you say that is Z k, it will be simply I E plus I S. I S is already known. So, everything is now systematic and you get all the impedance values. So, please go through these steps, very simple. With simplified networks, it will not be a tough thing to construct B matrix and to construct impedance matrix. That I will do in some later class, some numerical problems I will solve. But today I am going to just tell you, I have got this to summarize this lecture. What I am trying to tell is this, these are the basic relationships that we got. A I is 0, but this I is the actual current here, this current, not this part of the current. So, if you want to adopt loop analysis, then B will be involved, that is what we have done. Next time we will solve by applying nodal method. Thank you.